pieces, and maybe you could take it back and forth. You said it was all in the ether, ain't something you said you could feed her. She said she was nothing but eager, then you said.
So everyone, please mute yourselves. So tell me when to start, Harsh. Okay, so welcome everybody and good evening. So welcome to the second day of PyData Delhi Meetup, and we had a very awesome day one for the meetup yesterday, and I hope you guys learned a lot from the workshop. And I can see the views are going up and up. All of you must have been using open data source tools like Pandas, Scikit-learn, Matplotlib, Interact, and these kind of stuff. So these are open source projects which need a definite source of income and support for their sustainable development. And NumFOCUS, so this is where NumFOCUS steps in, and NumFOCUS is a non-profit 501c3 non-profit in US which supports all these open data source tools. So this is basically a NumFOCUS umbrella under which all these open data source tools come. And PyData is basically educational initiative by NumFOCUS, and more like a community for developers and users of open source data tools. And it has like around 160 plus chapters all over the world. Like it's pretty active in Europe and American side. And so PyData Delhi is currently like fourth or fifth largest in the world and the most active one in the whole Asia. So yeah, that's pretty exciting for us, and we've been working very hard since then. And yeah, so PyData Delhi was founded back in 2016, and since then we have done a lot of meetups. Like this is the 39th meetup and 3 conferences in 17, 18, and 19. So yeah, I think that's pretty much about PyData Delhi and NumFOCUS. Yeah, so this is a very unique time that we're living in the state of pandemic, and the NumFOCUS is the primary source of NumFOCUS income is dependent on the conferences, the conference series that um, you know that's happening on the that happens all over the world. But in the state of pandemic, that I don't see the conferences are happening all over the world. So obviously you can go to these links and donate to NumFOCUS, and every penny counts, no matter how big and small the amount is. It's definitely count because it's just a way of supporting the libraries that you've been using for so long. Yeah, so we are live on YouTube, and you can go to this link and just share this link with yourself. So the speaker for today is Nick Frosst, and he's on call with us today. And so Nick Frosst is a very interesting personality. I mean, he works at he used to work at Google Brain with Geoffrey Hinton, and so the most exciting part is he plays in a band, and so the band name is Good Kid Band. You can definitely check it out. So there's a link to the speaker in the description of the YouTube video. You can go and check him out. And yeah, more of that in a minute, because I think it would be better be introducing himself. Yeah, so questions. So the talk is gonna be about adversarial examples and why even bother. And obviously, I think that a lot of you are gonna have some questions to ask. So the best way to ask questions is YouTube chat. We have volunteers spread all over the YouTube chat, and we would be taking your questions on a rolling basis. And if the question needs the attention right away, we might interrupt the speaker and ask in between. But usually the questions would be put up to the speaker in the end of the talk. So yeah, code of conduct, and so in the meetups and conferences we follow a code of conduct. I mean, so but it's imperative that we should also follow this code of conduct in the virtual meetup like this one. And there's nothing much to be concerned about this, but you just have to be nice with everybody and ask relevant questions like to the uh, like uh, to the topic of the speaker is asking, and don't spam the YouTube live chat. I mean, that would be pretty much it about that. Yeah, so we love talks, and we are always encouraging communities and everyone in the community to give and talk about it. And we have also got some proposals, and we are currently reviewing them. So if you have a proposal for a lightning talk, you can just go over to this link and create an issue over there. And so yeah, we are everywhere on social media. You can check it out on all the major social medias, and we are by this handle PyData Daily, and you can just go and follow us over there for quick updates, because I think we have a lot of interesting stuff coming out in a few weeks. Yeah, so as said before that we have a public calendar, a Google Calendar for all the meetups and everything, like quiz events and challenges. So you can just go over to this link and subscribe to our Google Calendar, and you'll get a notification right away that when the next meetup is gonna happen. And we are quite active on Telegram. You can just go to this link and join a Telegram channel, and basically we update our Telegram before anything on the social media, and all the discussions and everything are going over there. You can ask questions related to data science and everything, and this is a good place to to be there. Okay, so there's been a wildcard entry in the today's agenda, so I must you know announce about this. So after Nick is gonna done with his talk, so a team member of ours, Harshita, she's gonna be presenting on practical look at open problems in federated learning, and it's gonna be an exciting talk. And I think like somewhat these two fields are connected to each other. I mean, I'm not sure, but yeah, it's gonna be an interesting ride. And so sit back, relax, and enjoy the meetup. So yeah, over to you, Nick.
Hey, can you all hear me?
Yeah.
Good, great. Okay. Well, first of all, thanks so much for having me. It's really great to see such like lively open source communities and not-for-profits contributing to the code that I make use of for machine learning and that we all do. So that's really awesome. Secondly, I have never been to Delhi. I would very much like to come. It looks really cool, but I am currently stuck in quarantine in Canada, as I assume many people around the world are. So this is the best I can get right now, but I really appreciate it. So thanks a lot for having me.
Yeah. You're more than welcome to come Delhi.
Great. Okay. I really would love to at some point. So maybe I'll send you a message if I can ever get out of here.
Yeah, and we're gonna save a spot for you on a stage also. Like, you know, you can play one of the songs.
I'll bring the whole band up. Yeah, great. Okay.
So I think you can just start your screen sharing.
Okay. Cool.
And while you're at it, can you do a quick little introduction about yourself?
Yeah, sure. Let me just get this screen up. Okay, can you guys see this?
Yeah, I can.
Great. Okay, and let me just go to present. There you go. Okay, cool. So yeah, my name is Nick Frosst. I've been working in machine learning for a couple of years now. I worked with Geoff Hinton in the Google Brain Lab in Toronto for 3 years, up until this January, actually, where I focused mostly on capsule networks, explainability, and adversarial attacks, and sometimes those things in conjunction. So that's some of what I'm going to be talking about today. But yeah, like you said, I also play in a rock band, which I don't normally talk about when talking about machine learning, but thank you for hyping up my band. That's a fun thing I do kind of on the side. Yeah, okay, cool. So a couple of points of order before I begin. Normally when I give talks, I like to ask questions of the audience pretty often and like get people to raise their hands to figure out if people are understanding what I'm saying. Obviously I can't do that in this situation. So if you have a clarification question, please ask it in the chat. And I've asked the guys to interrupt me so that I can like make sure what I'm saying is making sense to everybody who's watching. And if you have a follow-up question, just ask them in the chat and we'll get to those at the end. Yeah, so what I want to talk today about is certifiable robustness to adversarial attacks and what the point of those are and if there is a point. So first, a preamble. The talk will definitely be a lot of my opinion, and my opinions may very well be wrong. So if you take umbrage with something I've said, you can rest assured that you might be correct and I might not. Or you can ask a question and we can go back and forth a little bit. Okay, so to get to the main point of it though. So I want to be talking about adversarial attacks and a cycle that has been going on in the machine learning literature for like many years now. So first of all, yeah, this is a period where normally I would ask people if they know what an adversarial attack is, and then I would get people to like raise their hands to figure out how deep I should go into adversarial attacks. But I'm going to assume some of you don't know what they are, so I'll go over it. An adversarial attack is an input to a neural network or a machine learning system, but in the context of this talk, we're talking about neural nets, is an input to a neural net that was intentionally crafted by an adversary to mess up the network. So you train some network to do some task, and it does really well on the test set, and then someone comes along and they intentionally create an input that messes up your network.
I'm sorry to interrupt you. I think just a second. I think there's been some issue. So I think like we are seeing this window, and I don't think we are seeing the presentation mode for the slides.
Which window are you seeing?
So there's a Google Slides open, and we can see the slides in the gallery view.
What? Oh, that's the wrong. It says I'm sharing this screen. That's the wrong screen.
Yeah. I think
okay. Well, that's fine. Actually, I can just present on this screen.
Yeah, you can maximize the screen also.
Yeah. Wait, can you see it now?
Yeah, perfect.
So you saw ahead. There was big spoilers. You saw all the slides till the end. Okay, cool. Okay, well, thanks for. Okay, so here, this is odd. Yeah, it says I'm sharing this screen, but I'm evidently not. I'm actually sharing this one. So you can see it now. It's the first slide.
Got it. Yeah,
great.
Got it.
Okay, cool. That's fine. Okay, cool. So thanks for the clarification. Okay, so adversarial attacks are inputs that are intentionally crafted to screw up a network. Often when people talk about adversarial attacks, there's a whole bunch of assumptions that they make about what kind of things do and do not fall into that category. And we can get into that. But for the most part, the cycle that we've been seeing and the cycle that some of my work has attempted to address, and the cycle that is the main focus of this talk, is the cycle of defense creating and breaking. So this is where somebody creates a network, and then someone creates an adversarial attack to the network. And they say, hey, look, your network isn't as smart as you thought it was. I can make this very simple attack, and your network does really poorly. And then someone says, okay, that's fine, but I've like created a defense to that attack. And now I have a network with some property, and subsequently that attack is no longer going to work. And then they publish that on archive, and a couple months later, somebody else creates a new attack that breaks that defense, and the cycle repeats. So that cycle has been going on for since adversarial attacks were first published. So for several years now, that cycle has been ongoing. And yeah, what exactly that means for science and what exactly that means for adversarial attacks and neural networks remains to be seen. Some people in the past couple of years have seen this cycle and have attempted to get ahead of it by creating what they call certifiable robustness to adversarial attacks. So what they want to do is, instead of just creating a defense to some adversarial attack that was recently created, they want to create a network that has a provable defense to all adversarial attacks. So they want to be able to prove that regardless of what strategy you use for finding an adversarial attack, they want to be able to say that we will not be susceptible to that attack. And they want to prove that mathematically so that they're not just left to like random people happening to dedicate research cycles to trying to break that defense. So they want to be able to prove it. And that was a good idea. Like, that makes sense. You're seeing this cycle, you're trying to get ahead of the cycle by, instead of just creating a defense, you prove that your defense is going to work. So people have done that largely by looking at certifiable robustness. So certifiable robustness is often talked about as like epsilon certifiable robustness to adversarial attacks, is one form of having this provable solutions, provable defense to adversarial attacks. So the way that works is illustrated by this graphic here. And it effectively boils down to saying the problem with adversarial attacks is that they are small perturbations to the input that result in large perturbations to the output. Okay, so imagine we have an image classification system. We're classifying this image as a panda. The problem with the adversarial attack is that we can make very small changes to the input that you and I don't see, but that the network, like the logits of the network, of the classification network, change wildly based on the small perturbation of the input. Small here, when I say small, what I mean is the distance between the two things. So like the Euclidean distance between these two images. Images are just massive dimensional arrays, and there's a notion of distance between one image and another. And people were most upset about adversarial attacks because it turned out you could use this very small epsilon multiplied by some noise pattern. The resulting adversarial image looks exactly the same to you, and the network is convinced that it's now something else. It's not a panda anymore. It gets the classification completely wrong. So the way that they tried to do this certifiable robustness is by proving that small changes to the input result in small changes to the output. And that means that if you add this little noise pattern, but it's a very small addition, you're not going to have a drastic change in the classification space in the logits. You're just going to have a small change. And so you're not likely to get something that goes from being a panda plus a tiny noise to have it switching its classification completely. So here, if we imagine the high dimensional image space as 2 dimensions, and the way to do that is think about high dimensions and just say 2 dimensions over and over again in your head. So this is the 2-dimensional representation of some high dimensional space. And we have these decision boundaries, which are a consequence of having some final classification layer. We can imagine those decision boundaries as being some line. And we're just going to say that if the image is classified as a panda, the distance between that image that's classified strongly as a panda and any other classification is epsilon. And that means that we're going to have to change the image by epsilon in order to get some different classification. So that's the certifiable epsilon robustness. We have certified that up until epsilon, we will be robust to changes in the image. So this is often done with something called a Lipschitz constraint. So a Lipschitz constraint is one way of trying to do this certifiable robustness. And the way that works is visualized here on this graphic I pulled from Wikipedia in 2 dimensions. And this says, if we imagine we have a function, and the function is that purple line, and the function takes in x and outputs y, the cone that you see visualized there represents the Lipschitz constraint. And that's saying as long as something never falls within that cone, as long as the output of the function never falls within that cone, then we know that we will never have drastic changes in the function, right? We'll never have a huge spike. So you can see, you can draw that cone along the function. You can see nothing ever falls in there. And then you know that the slope will never be within that margin. And so you know changes to the input will never result in changes to the output. So this is done on the 2-dimensional. This is done on 2 dimensions, but you can do this in a neural net just with some high dimensional cone. So that's called a Lipschitz constraint. And there are various functions that do and do not fall into that. And you can do things to neural networks to make sure that they satisfy this property. So there was lots of people who did lots of research into Lipschitz constraints for certifiable robustness. Actually, this is kind of blurry, but there's a whole bunch of papers on this topic. And almost all of them use Lipschitz constraints. And it seems to be really promising for a while. It seemed like this was gonna be the way to break the cycle. But there's some fundamental things that I think have not been established about why we're interested in this in the first place. Yeah. Sorry, this is the part where now we're getting into opinion. Now we're getting into my own opinion. So one of the things is what exactly the notion of small is. So earlier I talked about small as being the distance, the Euclidean distance between the array that represents some image and array that represents some attack. And we want to make sure that those two things are small. And I think to begin with in the adversarial literature, people assumed that Euclidean distance equated to visual similarity. So that if the distance between one image and an adversarial attack was small, that meant it was imperceptible. And for a while, those words were kind of used interchangeably, but that's not the case. And our eyes are very complicated and fine-tuned systems that do all kinds of, can pick up on all kinds of things that are arithmetically very small. So this is a image I took from a paper by Justin Gilmer, who does great work on the topic. And he's here showing that there are various, like the visual, the percept of seeing two images can vary widely, even if they're equivalently far apart. So here, the image in the middle is the same distance away from all the images on that outer ring. So the one at the top, you can see it's just a little brighter. It looks pretty much the same. Like if I wasn't looking for differences, I might not see any at all. Whereas the image on the bottom is completely inverted, looks nothing like the image in the center, and yet mathematically they're the same distance from each other. Yeah. So what does this mean for adversarial attacks? It means that we were maybe worried about maybe we were using the proxy of distance as incorrectly. So the real issue with adversarial attacks was not that they couldn't recognize things that were close together. They recognized things that were close together as two different things. The problem was that we gave them inputs that to us we had no issue classifying at all. Like the panda in this adversarial attack still looks like a panda. You don't even notice that it's been changed. And so that is an issue. You're like, oh, well, I trained this neural network. It's supposed to recognize pandas. It's not even recognizing as panda. I can obviously see that it's a panda. That's an issue. My network is not as good as I thought it was. And we were using like distance as a proxy for visual similarity. But that obviously is not sufficient. It turns out that, yeah, distance is a poor proxy for similarity. And although in the study of adversarial attacks, for the most part, when you're adding small epsilons, yeah, it's small enough that you don't really tell. That's not a guarantee. And furthermore, the epsilon stuff, certifying that within epsilon, you're gonna not change your classification might even become a hindrance. So that is where we get into some of the work that I did with some collaborators at Google Brain, in which we created networks that had with resulting adversarial attacks that were within epsilon, but were not only visually dissimilar, but were also of an obviously different class. So here we have the clean input is on there's like two rows of clean input. There's SVHN, which is a data set of colored images. And then there's CFAR, which is a data set of small images of random classes. So if we look at the digits at the top, which is like a colored version of MNIST, we can see the clean images on the second row. And right above that, we see the adversarial attacks against our model. And so why don't we look at the last column that has an 8 as the clean input and the 9 as a deflected attack. So these two images are within a very small perturbation. They're within the standard perturbation that is used when creating adversarial attacks against SVHN models. So people would use this epsilon to show, hey, we can still attack this model. And yet here we have visualized a bunch of images that, like, if your certifiable model, if you had a certifiable robust model and it was certifiable to the epsilon that these are with, then you would definitely get these wrong because that 9 looks like a 9. And although it is within epsilon of an 8, it's still obviously a 9 to us. Same is true with the 8 and the 1. And if you go along, like the 6 and the 0, these are obviously classified by people as the target class. And so a certifiable model would necessarily get all of these wrong. Here's another example where I would stop to ask people if what I'm saying makes sense. But I'm just going to assume it does. Okay. So yeah. So what does that mean for certifiable robustness? That means that although certifiable robustness may be able to solve problems like this, in which adding the epsilon noise really does result in a visually similar adversarial attack as the input, and certainly hasn't changed the class, certifiable robustness also means that if you give it these models, you will necessarily get them incorrect. So there's a trade-off. And to begin with, that trade-off was made by the research community as saying, like, it's fine that we're invariant to epsilon changes, because as long as we're within epsilon, we know that the image will look the exact same. But that was shown to not be true by Justin Gilmer in this paper. And then furthermore, we are now showing that not only is epsilon not sufficient to say that it is visually similar, it's not even sufficient to say that it's the same class. So that means that your certifiable robustness model will definitely get things in the wild wrong. We've also done that same thing for CFAR, and you can see it kind of works, but like not as well. It doesn't work as well. So if we look at the truck and the ship on the rightmost column, you can see that it starts off as a ship and then it kind of flattened things out and kind of got rid of the water to make it look a little bit more like a truck. These ones are definitely up for debate. We actually, so in this is the paper where we present this work. And it was done by it was first authored by Yao, who's an amazing student and doing really great work. We actually do a human study on these as well. And we show that we just used Mechanical Turk, and we showed that the adversarial attacks really are classified by people as the target attack, making them no longer adversarial in some sense of the word, which is why we use the term deflected. This paper turns out to be a convoluted one, and it's on archive and nowhere else so far, but we are working on it. So that kind of takes us a couple steps back. So what I've tried to argue here is that adversarial attacks were a problem. There was a cycle of attack and defense. People tried to get ahead of that by proving robustness to a certain epsilon, to a certain change. They did that because they thought that as long as an image was within epsilon, that means that it almost certainly looked the same, and certainly it was the same class. And we showed that neither of those were really true. Neither of those are true. So a certifiable robustness, yeah, it may protect you from epsilon, from adversarial attacks within epsilon, but it also is going to have all these inputs be wrong, like the inputs we've created. And that kind of gets us to take a step back and say, well, why were we even concerned about adversarial attacks in the first place? What really was the issue? And a lot of times when people talk about adversarial attacks, they talk about security. And they talk about like, oh, if we're deploying neural nets in real world systems, we have to make sure that they're going to behave reasonably and that they won't be vulnerable to attack. And so we're gonna try to create defenses or provable robustness to solve this problem. But I'm beginning to think that it's not really a problem in the first place, and that the main issue here was not a security threat, but was in fact kind of a philosophical shock to the people who were working on neural nets. And that they trained a neural net, they got it to classify one set of things, and it did really well on the test set. And then they said, okay, well, therefore it's classifying the way I would classify. And so I've created something, on the road to AI, I've made some computer do a thing the way I would do it. And that's really great. And then someone comes along and says, hey, here's adversarial attacks. Your network is behaving wildly differently than you thought it would, because you're getting these Panda images correct, and it's not. So that's an issue. And it's the response to that like philosophical shock of saying, oh shit, like the network is not behaving the way I thought it was, more so than it is a response to some security threat. So the security threat is an interesting one. So lots of times when people talk about adversarial attacks, they say, well, imagine we had a driverless car. And imagine that you went up and you made a small epsilon change to a stop sign. Now your driverless car couldn't tell that the stop sign had been changed. You couldn't tell that the stop sign had been changed, but your driverless car would no longer see it, and you might just drive straight through, and wouldn't that be an issue? But it turns out there's a lot easier way to mess up a driverless car. If you want to, you could just go knock the stop sign down. And that would cause as much trouble without you worrying about epsilon robustness or running up to the stop sign and making a small change. And it would have the same effect. And people might not notice the same way they don't, because we're very robust to things like stop signs being knocked down. Like if you come to a streetcar and the traffic lights are out, you know what to do, right? Like there's a standard protocol. You're very robust to changes in the system, and a driverless car wouldn't be. And the robustness is the problem, but it's not a robustness to some epsilon perturbation. It's a much broader sense. Like it's a robustness in the human sense of the problem. Yeah. So it turns out this type of thing seems to be there in almost all adversarial attacks that I've heard talked about. Now, when I say this type of thing, I mean, it normally turns out that there's an easier way to break a computer than with an epsilon attack. I mean, you could normally just break the computer and that would have the same effect. So was it a security threat? I don't know. I keep a running list of times in which an adversarial attack was used in the wild. And so far the list is one. So far I have one example of this. I mean, hacking obviously has been around for a long time, but when I say an adversarial attack, I mean someone used the work that has been published by the adversarial research community to do something malicious. And the example that I have that was I only got recently. And that was an attack that was done against a security company called Proofpoint, and they had a spam detection email model. And the way that this was, so they have, it takes in an email and it tells you whether or not it's spam. We actually have these, they're actually really great. There's been, I mean, that's a very interesting security problem. There's been a war going on in the background between email providers and people making spam for years now. And for the most part, I'm feeling like the people making the detectors are working. Because like, I don't get spam very much anymore. Not the way I feel like we used to. So this is different than the image domain. This is in the language domain. And exactly what small means in the language domain is complicated enough for debate. But mainly it's, mainly what an adversarial attacker would be trying to do would be trying to create a sentence that they want to deliver to an email user, and they want to have it not be detected by the machine. So that's actually quite a bit different than the adversarial stuff we talked about earlier, because it's not important that the email isn't noticeably perturbed. It's not that the attacker started with a real email and then changed it slightly so that it wasn't detected, right? They were able to craft an email from out of nowhere. They crafted their own email with their own like content that they wish to deliver, and then they're making perturbations to it. So that war has been going on for a long time, and people have been doing smart things like spell words incorrectly or like put dashes between things, and then you get those through every now and again. But this example that I heard of recently was very much an adversarial attack. So what it was is some people found that the Proofpoint company, they were actually exposing the numbers that they were giving for their emails. So like the confidence that they had in it being spam. So then they just got the program, sent a ton of emails to themselves to create a labeled data set. Then they trained a model on that labeled data set. And then they created an attack for their own model, and they showed that that transferred to the other model. So that's like a standard black box adversarial attack. The difference is here, though, is that, again, it wasn't bounded by epsilon. And it wasn't done in the normal way that adversarial attacks are done, in which you like back propagate the error with respects to the input, and you make a change in the input to maximize the error. It was actually done by just like randomly flipping words in and out and seeing which ones had the biggest effect, and then making an email that had those words but was able to deliver the content. So it is a black box attack. It was in the wild, and this is now the one that I'm going to keep on this list of times when adversarial attacks came around. But it had nothing to do with certifiability. It had nothing to do with distance. It certainly had nothing to do with like some epsilon between some real input and some perturbed input. They just created one out of thin air, which is quite a lot different than the assumptions that people had made when talking about the attack breaking and defense breaking and talking about certifiable robustness. So yeah, that leaves us with a philosophical question of saying, what does this mean for the field? What does it mean for the field of machine learning? What I've been trying to argue here is that people saw an issue in neural nets. They tried to fix it. It didn't work. They spent a whole bunch of cycles a whole bunch of like years going in a cycle. They tried to make certifiable robustness. The certifiable robustness hindered the network because it made it bad at examples that we have shown exist. So it makes it mean that those ones get it wrong. And it solved a problem that didn't seem to be a real problem in the first place. In that, again, epsilon robustness is not a thing that I've seen in the wild. So yeah, a huge number of research hours have gone into attempting to solve a non-existent problem with a poorly motivated solution. So what does that mean for machine learning? What does that mean for AI research? An optimistic view is that that's fine. Is that the Lipschitz constrained stuff. So the stuff I talked about earlier with the like cone and saying a small change in the input results in a small change in the output. I've seen that referenced in many other places within the machine learning community. So it turns out that you can use the Lipschitz constraint to make general adversarial networks better, because you make sure that like small changes in the latent space don't result in huge changes in the output space. And that means you get nice smooth generators, and that's good. It means that you can make invertible networks more invertible. And invertible networks are where you can run them forwards and backwards, and you can recreate the input from the output. And that has all kinds of cool properties. So it might be the case that the work done on adversarial examples, though poorly motivated and solving a non-existent problem with a solution that definitely hurt the final goal, it might have been the case that the research on that created more things and was able to be adopted into other fields of machine learning and with huge success. So that might have been the case. Every now and again, when someone tells me that they're working on Lipschitz stuff, I ask them if they found out about the idea of Lipschitz constraint through adversarial attacks. And the answer is so far no, but there's still a chance that maybe this work has motivated them in some good way. So maybe that's the normal way science progresses. Maybe alchemy begets chemistry, and maybe we ought to do science by just doing what interests us and what we think is relevant, and not spend too much time thinking about whether or not it actually is. Not spend too much time thinking about if it's actually grounded. We ought to just pursue things freely and see where they get us. And that might be the case. I don't think that's what happened with adversarial examples. Unfortunately, I'm a little, what I kind of think is more likely to happen was that ML research is in an interesting place and academia is in an interesting place. And it's a place in which you're constantly having to justify why the work you're doing is relevant. And if you're always having to prove to people that the stuff you're doing is super important and you need funding and you still need a lab and you're always fighting for it, then it's very easy to fall into things like, oh, it's, the research is super vital because networks out there are being attacked and we have to stop them from being attacked. And to not spend too much time thinking about if that's really the way in which they're getting attacked, whether or not the defense is really going to help, what the problem really looks like, because you need to justify it. And I don't think that's a problem with individual scientists or I think that's a problem with the culture that the climate we're in terms of scientific development. And I don't know which one it is. I don't know if that's the right way to go about it. I don't know if that's going to create the most research, the best. I don't know if that's going to get us to AI the fastest. So far, the progress seems to be good. So maybe, but I don't know. I think I'll leave it for there for now, and happy to take any questions if anybody has them.
Yeah. Thank you, Nick, for the talk, and I think we have some questions over the YouTube live chat.
Mm-hmm.
So
should I
I'm just gonna start with the first question.
Oh, can you read it out? Oh, great.
Yeah, I'm gonna read it out. So
Great.
the question is, so there's a question. So am I correct in assuming we use Lipschitz to figure out a threshold for epsilon, which image only gets changed certainly but changes classification for the model?
Sorry, can you read that once more?
Exactly. No worries. So am I correct in assuming we use Lipschitz to figure out a threshold for epsilon, which image only gets changed certainly but changes classification for the model also? Okay,
so when people are doing Lipschitz constrained certifiable robustness, they don't use there's a strange connection there. So you're going to create a model that is certifiable robust to some epsilon. If the epsilon was huge, if your epsilon was, if your epsilon was massive, then you wouldn't have a classifier. You would have a constant classifier, right? I can make a certifiably robust classifier by always outputting one class, and that's robust to all epsilons. So instead, what you're going to do is you're going to come up with some epsilon that you think is reasonable, and then you're going to show we can have a Lipschitz constraint that enforces Lipschitz of that epsilon, and then we can show that we're robust to that epsilon. And the way that epsilon was chosen was I don't know, people use 0.01 a lot. And for different data sets, there's different numbers that people kind of use. And they're roughly about some intuition about oh, if you change it within this epsilon, you can't tell. And that it's kind of hooked back into the visual similarity thing. But it's not based off of it. It's more like a heuristic for saying, if we change the model this much, then we can't see the difference. And that kind of implies what I was starting out with at the beginning, with saying that the real issue is not the distance. The issue is the visual similarity. And we use some epsilon to as a proxy for visual similarity, but that is insufficient. So to answer your question, we don't you have to decide as a researcher when you're publishing a paper what epsilon you're going to use, and you're going to enforce that epsilon robustness with a Lipschitz constraint of that epsilon. But you kind of decide it based on what the that's just a number that you use based on what the research community thinks is reasonable. Yeah.
Yeah. All right. So the next question is there a way to take some lessons from the representation learning to figure out how these small perturbations get represented in high dimensional space after the convolutions, etc.?
Oh, I'm sure there is. In that, yeah, I guess from the representation learning is another field in which I feel like we as researchers are putting our own biases into what we want the model to do. Like I've often seen people talk about like disentangled representations. And they try to do this for like image generation, where you want a latent space where like there's one dimension that represents whether or not the face that you're generating has glasses, and another dimension that represents whether or not it has a beard. And we talk about those as being disentangled. But those are just disentangled because like those are concepts to us. Like it's a clear concept that a beard, you can remove your glasses and you can shave your beard. And so those are like seem like they're orthogonal to each other. And so we want a network that has similar representations. But we don't know if those things are correlated in the image generation problem and the face generation problem. That's a human bias that we are expecting our networks to have, and we're adding things in to make it so that they have that bias in representing things. Similarly, the issue with adversarial attacks is that we have a bias about what should and should not be represented when we have some representation space, and we don't think that the epsilon noise that is added to adversarial attacks should be represented, let alone detected. So they're definitely related problems in that, saying representation space, we want it to pick up on certain things. We want representations to be good for some reason. We want them to separate the classes, or we want them to separate the features in a way that makes sense to people. And the adversarial attacks are saying, we're picking up a representation that we don't want. And that is the representation of the adversarial noise. So if there was a way that we could get a network to represent the features that we want, and only the features that we want, and the features that humans pick up on, then yeah, maybe we would solve adversarial attacks in that sense. But that's kind of taking away what the power of neural nets do. Like neural nets are so great because we don't have to do feature engineering, because we don't need to make sure what feature, when I train a net to classify images, I don't even know how it does it. I'm not telling it to recognize like an eye, a nose, and an ear and put them together to recognize the face. I'm just telling it to learn things. And it happens to be that works really well for test images, but then it also does these things like doesn't notice adversarial changes. So the two are definitely related. What work can be taken from one and applied to the other, I'm not sure. I haven't seen, as far as I can remember, I haven't seen somebody that's addressed adversarial attacks with like very meticulously done internal representations. But I'm sure that's an interesting research direction. Yeah.
All right. So yeah, so just jumping to the next question.
Yeah.
So has there been a research? Okay. So has there been research on ways to find the ideal perturbation of a particular epsilon, which result in the largest output changes in the logits?
Has there been? Yeah. Okay. So I guess when you create an adversarial attack, the way you do it is you do the opposite of what you did to train the network. So when training a network, you have a whole bunch of numbers that represent the weights, and you do gradient descent to minimize the loss with respect to the weights. And when you do an adversarial attack, you freeze all the weights, but then you do gradient descent on the attack, on the input, to maximize the loss. So you do the opposite. And so it's gradient descent the way that it's the same operation. And so in a way, that's a heuristic for trying to find the maximum change in the outputs that you can get for the change in the inputs. So all the attacks that exist, like, yeah, there's the standard, like there's a regular attack where you just take one step in the direction of the gradient with respect to maximizing the loss. There's all kinds of other attacks where you bounce around a little bit. There's one attacks where you first add some noise and then you do gradient descent on the image. And all of those are heuristics for finding the maximum change you get out of the output with respect to that epsilon change within the input. So they're all kind of trying to do that. Are there any ones that have is there a way of showing it? Like, no, there's no way of proving that within some epsilon ball, you have found the maximum image, in the same way that there's no way of proving that with a neural net, doing gradient descent will eventually give us the ideal weight setting. They're very similar problems. So we can't prove that we can find the maximum one, but all of the attacks are heuristics for attempting to do that. Yeah, these are good questions, by the way. Thanks a lot, everybody.
Yeah. So jumping to the next question, and it goes something like, in the natural language case, do you think the internal representation of the normal versus attack emails using, say, BERT would have high cosine distance between them?
Read once more. Do I think in a BERT model, the representation between, actually, sorry, can you just read it again? Yeah.
Yeah, sure.
Yeah.
So in the natural language case, like NLP, do you think the internal representation of the normal versus attack emails using a BERT model, for example, would have a high cosine distance between them?
At what stage in the network? I mean, again.
So I think basically the question something like the attack emails, the noise and the normal input would have a high cosine distance between them. For example, using a BERT model in NLP.
Oh yeah, well, if the BERT model was, so if you made an attack against a BERT model, so like it's hard to do email adversarial attack because it's not smooth, right? So you can't just like take a step with some respects because it's not a continuous input space. It's a discrete input space. But you can make adversarial attacks. And if you made an adversarial attack against a BERT model, you could target an internal representation the way you can target the output, the classification. So it would be possible to create an adversarial attack whose representation space, whose representation was very similar to the representation of some other image. In fact, some of the work by my co-author, Sarah, and friend of mine, Sarah Sabor, who was on that paper that I mentioned earlier, some early work that she did was showing that adversarial attacks could attack representation space, so that it's not just restricted to affecting the classification. You can get any image to be like represented arbitrarily in the representation space. So if you were making an attack with emails against a BERT model, I could imagine that you would be able to create an attack that read completely differently but was represented in the same space. I imagine it would be difficult because you're in a discrete domain, not within the continuous domain in which adversarial attack research is normally done. But I think you probably could. But some of my other work is showing that when you're doing just adversarial attacks against the logit space, the resulting image, the resulting like input, is very far away from regular data in the representation space. So I have a paper with Nicholas Paperno on representation space and soft nearest neighbors, and we show that adversarial attacks are handled very differently in representation space when they're made against the logits. And so that to me implies that unless it was intentionally done, and it would be difficult to do it intentionally because of the discrete characteristics of the input space, it would probably have a very high cosine distance and it would be far away. And the work that I did with Paperno was using that property, saying that these things are like adversarial examples are normally far away from stuff to create an adversarial attack detection method.
Yeah. All right. So I'm hoping that you are ready for some questions. We have another question for you.
Yeah, sure.
So the question is there a way to counter the piecewise linearity within deep learning models that would inherently cause such massive effects in vector space with such minute perturbations?
Is there a way to do that? Is there a way to do that? Yeah, I mean, so the nonlinearity is exactly what does this. It's the fact that you can have small, like that's what gives us the non-Lipschitz constrained networks. And the Lipschitz constraint stuff is one way of trying to counter that. I don't think targeting like just you couldn't get it with just changing the activation function of the neurons. Like you couldn't get a Lipschitz constraint out of doing that because although suddenly you don't have a piecewise function in your activation, you're combining all those things. And so you could have a couple that like all the activations could have very small changes, and yet the activation in the higher level, because of the multipliers on there, could be totally different. So you could still end up with something that wasn't Lipschitz constrained. So I don't, so you're right in that it's the nonlinearity that's doing it. But just changing the activation function I don't think is the right solution. And that's not what the people doing Lipschitz constrained neural nets use.
All right. Thank you. So just let me just have a look at the YouTube chat.
Mhm.
Mm,
Also, yeah, sorry,
I think, yeah.
I can
So
stop
I think
presenting.
like we're done for the questions now. So I
Great.
think like we're done for the questions. So so volunteers, can you confirm with me? Like, do you have any questions?
Hmm?
I have a question for myself that I wanted to ask. Like,
Oh, sure.
yeah. So adversarial attacks are basically adding noise to the data and fooling the systems and networks like what the thing is not, and like the panda scene that you showed us. So there are like different types of data available, like image, audio, video, and sequential data and stock prices and everything like that. So I'm just guessing, I just wanted to know like which type of data is most susceptible to adversarial attacks.
Yeah. Yeah. So I can tell you which type of data is used in adversarial research, right? And that is images. We use images for adversarial attacks.
Yeah,
Like when people
exactly.
talk about adversarial attacks, unless the paper says something about adversarial attacks in a different domain, if the paper is certifiable robustness to attacks or like a new attack, it's almost always images all the time. And the reason for that is not that like it's not that the most important models in the world are image classification. It's not that like if you're a hacker and you want to make the most money at adversarial attacks, you make an image classification attack. Like it's not any of those reasons. It's that it's very easy to create a thing that gives you as a researcher that philosophical shock of saying, oh, the network I trained that I thought was doing really well is in fact doing poorly on things that I think look normal. So, and the reason for that is that the notion of epsilon similarity, like it kind of matches up with visual similarity. And so you can make something that's an epsilon change and you can't tell. Now, not all the time, as we've shown, but for the most part, you can make that assumption. And so that means like mostly people do adversarial research on attack images. So far as that, yeah, when you say adversarial attack, it is synonymous with images attacks unless otherwise specified. So, I mean, it's also the case that they're the most, that's a continuous space, and that makes the problem a lot easier because you can calculate the gradient, and then you can take a step within that gradient with a learning rate of something. It's just a lot easier than doing it in a discrete space. So that email attack that I mentioned earlier as being an example of a real adversarial attack in the wild, they didn't take a gradient step. They just flipped, like added and removed words to see which one affected it. And so that's like a lot harder to do. So like what's the most susceptible? I don't know. And I would kind of say they're all equally not susceptible because the problem's kind of made up in the first place. So like it's not really, but what is the easiest to study and what is studied the most? Definitely images. And that is, yeah, because it's easy to get a philosophical shock and it's a continuous space. So you can make assumptions that like kind of match on to visual similarity. Yeah. Makes sense?
All right.
Sweet.
Yeah, exactly. So, so is it safe to assume that the most of the research on adversarial is done on images, but there may be chance that all different kind of data like images or like audio, video, and serial data and would be susceptible to adversarial. So is there a resource? Yeah, is there a resource that that audience can look over if they want to follow the adversarial research and everything?
Yeah, sure. I mean, so in particular to your question, some work by Yao Quinn, who is a co-author of mine. She did some work on audio attacks. And they're quite cool because you can you hear them and they sound the same to you, but your Google Home will pick up something completely differently. So those are very fun. So yeah, you could look at that as an example of good work within the audio domain. But there's tons of work for all kinds of domains. And in terms of, so the argument that I've laid out here about like the kind of philosophical one, I is not in a paper anywhere. It's the philosophical result of a paper that Yao and Geoff Hinton and Colin and I worked on, which is called Deflecting Adversarial Attacks, which is on arXiv now. Deflecting adversarial attacks. There's also the stuff by Justin Gilmer that I referenced, and that's been really important for having my understanding. And he's written a couple of papers that talk about he has one paper called Motivating the Adversarial Game. And that's a great paper that talks about some of the issues that I've alluded to and talked about. Yeah.
All right. Thank you. So I think that's good resources. So
Great.
meanwhile, we were going with the discussions. We got two more questions on the YouTube live chat. So
Oh, sure. Yeah. All right. Let's do it. And then I'll stick around for then there's a talk afterwards that you said, and I'll stick around for that. So I'm excited for that.
yeah, sure.
Great.
That would be so humble. So the question is there some way to use dark knowledge, relative prop distribution concept by Hinton to make models more robust to these attacks?
Yeah, dark knowledge. What a name, eh? He's really got a knack for naming things.
Yeah.
Dark knowledge. Yeah, I remember talking to him about that one. So dark knowledge, for people who don't know, is like, it turns out I think the experiment that he first did when he coined the term was that if you take one network that's like your teacher network, and then you train a student network based on the logits of that teacher network. So that's like standard distillation is what it's called. Instead of training on the classes from the input, you train on some combination of the classes from the input as well as the logit distribution from the teacher network. So that's distillation. Dark knowledge is then where you don't give it all the information. Like when you do your distillation, you only show the student network ones and sevens. If you're imagining you're classifying MNIST, you only show the network ones and sevens, but you give it the whole logit distribution. So you don't ever show, hey, like student network, this is a 3, but you do say this 1 is more like a 3 than this other one. And this 7 is more like a 2 than this other 7. So you give it the information, and that's called like the dark knowledge, because you're not showing it classes, but you're giving it these like these relative bits of information in the form of the logits from the teacher. And then it turns out that if you train a student this network, it still does a pretty good job at recognizing all the things it's never seen. And that's called like dark knowledge. So is there a way to use the dark knowledge from a teacher network to get robustness to adversarial attack? There has been work on distillation as a means of adversarial defense. That is work that was involved in that cycle of attack breaking and attack creating. So that was work that's like the distillation paper. I remember someone's like, oh, we solved adversarial attacks with distillation. And then someone says, no, you didn't. We just like changed the optimization a little bit and we still get adversarial attacks. So yeah, there's work. It's in the cycle. It didn't solve it. Yeah.
Yeah, all right. I think that answers the question.
Cool.
So the next question is, what about radial basis function based networks for decreasing susceptibility against adversarial?
Radial based networks?
Radial basis function based networks. Yeah.
I don't know what a radial basis is, so unfortunately I can't answer this question. Sorry.
Okay.
But I'll Wikipedia radial basis later and I'll learn something, so thanks.
Yeah, no issues.
Yeah.
So I think we have the last question for you. And so the question is, some additional priors given to networks, would they help in preventing? For example, besides image, we supply the image gradients.
Oh yeah.
So more like a warning to the network, like, okay, you're gonna have an adversarial attack. And
yeah, that's a cool idea. Yeah, you could. So actually, that's interesting. So you could take a network, you could give it an image, and then you could also give it the gradient of that image. That's a cool like Ouroboros-ing. You're like taking the model and giving it some information about itself. That could help. It wouldn't. I'm quite convinced it wouldn't solve the problem, because I'm sure what you would then do is you would just include that. Gradient in your adversarial optimization, and you would end up with a new adversarial attack that took it into account. Normally, the way the adversarial defense stuff works is that you just add the defense into the adversarial optimization, and you get a new attack. So the work that Yao Quinn and I and Hinton and Colin did, we've augmented a network for adversarial defense. But the reason why we think it gets ahead of the cycle is that the result of the adversarial optimization looks like the target class. So even if you add the defense in, you still get something that looks like the target class. And we did a human study to show that that's the case. And that's our solution to getting ahead of that cycle. But for the most part, when you just add something in that's like more information, it will beat a standard attack. But then as soon as you add that into the adversarial optimization, your defense is now broken. And then someone like Nicholas Carlini will come along and publish a paper saying that your defense is broken, and you'll feel kind of bad. He's done that a whole bunch. He's great at it. Great work. So yeah, it could work. My intuition is that as soon as you add it into the adversarial optimization, it wouldn't. but it's definitely in the right, like I like that idea of giving the network more information about itself and trying to get it to solve the problem. And that's what we did, a similar approach to what we did, is where we take the output of the image and we feed it back in, and we do this kind of Ouroboros-ing that I quite like. Yeah. Cool.
Oh, okay. So yeah, I think that's the end of the questions, and I think we had good questions so far. What do you think?
Those are great questions. Thanks everybody for obviously paying attention. I really appreciate that. Cool.
Yeah. All right. So I think we're gonna take a 2 or 3 minutes break, and after that we're gonna start with Harshita's talk. So Harshita, while and break, you can prep your slides and everything, be ready with everything. So I think we should have some random discussion to kill the time till then. So yeah, Nick, tell the audience more about you or your band.
Me or my band. Okay. Yeah. So I went to the University of Toronto, and I did a double major in computer science and cognitive science. And the cognitive science stuff,
great.
I found super interesting and still think about a lot, and still find that it's relevant to my work in ML. After that, I went to Google, where I worked as an engineer for a year before switching over and working in Hinton's team, where I was for 3 years up until this January. And now I work at a startup. Well, so it's still doing machine learning stuff. And doing research, but so that's kind of what I've been doing in ML. And I have a particular interest in adversarial attacks, in explainability and capsule networks, and recently language models as well. So those are kind of my areas of interest. In terms of music stuff, thanks for hyping my band. Feels great. I play in a band called Good Kid. We play like fast indie rock stuff. These guys have been nice enough to listen, so I appreciate that. We're actually everybody in the band is a programmer, and the drummer actually worked at Google with me for a while, and now we work together still. And the other guys work at various tech companies. So yeah, and we have a new single coming out in the next little bit, and an EP coming out sometime after that, and a video coming out, and we got a bunch of stuff going out. So yeah, that's kind of what I do in my spare time, and I find it very enjoyable. I really like the combination of music and research stuff. It's very
I mean, exactly. You don't want to all your time devoted to the tech. You need to look at other things, and that freshens your mind. And it's great to hear that most of the people in the band are programmers. I mean,
yeah, it's pretty funny. Yeah, we're a bunch of nerds, but it's enjoyable.
Yeah, that's good. So I think we should start with Harshita's talk. Harshita, are you ready?
Yeah, as ready as I can be.
All right. So I think you should start sharing your screen.
Sharing.
And please give a little introduction about yourself.
Great. Just give me a sec.
Sure.
Is this visible?
Yeah, I can see it, and I think you can click on the present. That would switch to the full screen. Yeah.
Okay. All right. Thank you so much, PyData Delhi, for having me. So, hello everyone. My name is Harshita Diddee, and I'm a pre-final year CS undergrad, and who's very passionate about privacy-preserving architectures. I'm novice at the game, but I'm currently a research intern who's exploring a certain configuration of federated learning. That's the specific domain within privacy-preserving AI that I'm very interested in. So I'm currently exploring a particular setup of cross-silo federated learning. And so, I mean, the agenda for today's talk is, I think, less academic and more experiential based. So I've had some development experience in federated learning. And today what I aim to do is by the end of the talk, you have a certain idea of 2 common open problems in federated learning, and that you're able to sort of map them from the experience that I have and sort of connect them to the open problems in federated learning that exist in today's time. And I also acknowledge the fact that a lot of you may not have like a lot of background with the pre-hand knowledge about the federated learning machine, like the learning construct, the entire pipeline. So I'm going to just briefly introduce the concept a bit, just give you a small definition of what federated learning is, and then aim to like encapsulate what is the motivation behind engaging in the development of federated learning architectures. After that, the second part, I'm going to discuss like the basic this demo example with the project that I contributed to in the last year, and I'm going to use that to connect them to some open problems that I feel federated learning currently has.
So hate to interrupt, Harshita. Can you be a little bit slower?
Oh, okay. Oh, sorry. Common problem with me. All right. So I'm going to begin with introducing the concept of federated learning. So by definition, federated learning is like a collaborative learning system. And the way that this system, the way that the term that justifies this collaboration is the fact that multiple entities, multiple clients are involved in the machine learning cycle of a federated learning system. So when I say the machine learning cycle, I don't necessarily mean a machine learning cycle. Any cycle where you're sort of learning, where the learning objective is to learn, the parameters, the model parameters of either a deep learning network or a machine learning network, or even like any basic like machine learning data structure. In that kind of a setup, when you have multiple entities. So when I say multiple entities, the current system of federated learning, the entities are usually defined as smartphone users or IoT devices. So, we were discussing Google, like voice assistants and home assistants. So these are actually a very common client consideration when we're talking about a federated learning setup. And then, of course, even organizations. There's a new definition of federated learning. It's called the cross-silo federated learning, which actually considers an organization to be as a client in a federated learning setup. And the idea is that these clients, they sort of collaborate to work under the coordination of a central server. Now, this central server is the server that houses the learning objective. So this is the server that houses the machine learning or the deep learning model that you want to train collaboratively. And all of these, clients, all of these clients that could be, scattered across the entire globe, for all you know, they are contributing to the learning of this model that is, the model that is housed on the central server. Now, traditionally, where federated learning sort of distinguishes itself from the traditional setup is that here, each client's data actually remains with the client itself. So in this case, so if you take the case of an organization, it's like multiple organizations are collaborating. Consider Amazon, Netflix and Amazon Prime, Netflix and collaborating to build a recommender system. But both Amazon Prime and Netflix are not giving out their data to a central server. They're only sort of giving the learning that they have on that data to the central server. So to sort of clarify what I mean by learning, if you look at the last line, I've sort of put a statement in bold, and that is, instead, learning updates intended for immediate aggregation are used to achieve the learning objective. So here, what I mean by learning updates is that every client, once it has like some local data, and once it trains its local data on a model, it has some learning. And by this learning, we actually mean the model parameters. In their most basic sense, these are the weights of the model that you have trained on your client. And these weights encapsulate all of the learning that that client has achieved by using the local data that he has. Now, with this learning, you could actually achieve inference. You could actually achieve, if you had the model architecture and you had these weights, you could achieve inference, and you wouldn't need the training data that this local client has. So this is, in my opinion, the core of federated learning. Having the data is not an essential to now taking advantage of the learning that you want to leverage your model with. And that is where we take the learning updates of all the clients. So what we essentially do in a federated system is that all of the clients, they sort of train a model on their local data. They take the learning. So the learning updates could be weights, gradients, sometimes even deltas. Take those weights and then send them for like some kind of aggregation. Now, this aggregation by simple sense means that it's a sum up of all the learning that you've had across all of the clients. And what it essentially means that even though you do not have access to all of the data of all the clients, you're leveraging the learning from all the clients by sort of summing up the learning that each client has had individually. And now this sum of like knowledge can be used in like multiple ways to benefit your global model. The most common way of doing that is through federated averaging, where you take the average of all the so the sum up of all the learning that you've had, you average it out, and then you update the global parameters according to this average learning that you've had. I'm going to explain a bit more about this, the entire pipeline in another slide. But before I go more into that detail, I'm going to just try and sort of run you through what is the motivation behind, developing federated architectures. Now, one common, everyone can actually, I think, put their like presumptions to this, that definitely federated learning, supports the privacy of preserving the privacy of the user. It is a user-sensitive machine learning inference pipeline, where because traditionally, what machine learning systems would actually do is that they would take the data of a client, they would send it on to a server, they would pre-process it, they would feed it into a network, and then give you an inference. And that inference would be sent back to the client. And that's how the client would avail the privilege of whatever AI service he or she is using. Now, this, of course, is not privacy preserving, because whatever data the client is sending to this averaging server, this particular data could be sensitive data. And even unintentionally, this third party, this cloud service, which is pre-processing the data and running the inference on this data, even unintentionally, they could breach the data, they could leak the data, and of course, then there's the concept of malicious attacks on the third party for people from agents who would want to tap into the knowledge of that data or use that data for malicious intents. Now, federated learning sort of eliminates this problem from the root. When you're not sending any data to the server, you are not really afraid of breaching any privacy of the user to that extent, because all of the data is stored locally on the client's device. So this is the first phase of what federated learning does. An equally important motivation for developing federated architectures is the lack of centralized data. So in traditional machine learning or deep learning systems, what we would want is that to begin with, we would want a massive data repository. A massive data repository means that you would want to have diverse data. You would want to have as much data as possible, so that the first time you did come out with your model, like when you ran testing on that model, the testing accuracy wouldn't be bad. But in federated systems, that's not essentially the case. In federated systems, you can actually start out with even randomly initialized weights. And this would mean that your initial testing accuracy is actually very, very poor, or your testing loss is very, very high. But if you look at the first class of traditional machine learning systems, it is very difficult to create that massive data repository. So if you're actually working with very distributed system, a very distributed data distribution, then it would actually be useful to iteratively improve the model by using learning from data, like on the fly. Every time that you got some data, you would use that data to improve your model bit by bit. And maybe after you've achieved like a benchmark accuracy with the data that you're training your model on, after that, you go sort of global with your model, which is usually how a software lifetime development cycle of a federated system goes. Sometimes they start with like, this is not the case always, but a lot of times you can start with like a randomly initialized model, which will give you like a really high loss. And then on the basis of that, when you start getting some data from the clients in the alpha beta testing phase, you keep taking that data from the clients. You don't keep the data with yourself. You just leverage the learning of the data on those clients. You improve your model a bit by bit, and you will see that iteratively the loss on the global model starts decreasing. So this is pretty much the main motivation behind which federated learning architectures are the most relevant to me. And then I'm going to come to the experiential tool that I was talking about. So I'm a novice at federated learning technically, but the development experience that I've had in federated learning, I've had it with a tool called Visionaire. This was a project that I contributed to last year. And the application is actually, it's an Android application. We used a TensorFlow and the TensorFlow API for Java to build this. And the application basically allows the user to click an image of his or her surroundings, and it returns the air quality index of the region by the image that the user has taken. So there's a very simple deep learning model that's running under the hood, and it runs so it takes the image, does some pre-processing, and then gives you the inference, and that inference is the AQI of the area that you are in. And it's a hyperlocal estimate, so it's very personal to the user because it's the user's image that is being used for this kind of an inference. Now, if you see the animation that's running here, it's pretty much a sum up of the federated learning cycle that I explained before. If you see the 3 client weights that come in the middle, these are basically consider 3 clients who are sending their learning to like a common place. Now, these learnings are aggregated into that yellow quadrilateral, and that summed aggregation, once averaged, is sent back to the client. So this is essentially how the federated learning cycle generally moves. You have a global model, you send the global model onto clients, clients train their model on their own local data, they send that learning to a server, and that server will average the data. I would average whatever learning it has. So in this case, would average the weights of the client weights, of all the client weights, and then update the global model with these averaged weights. So even though you're not essentially taking any data from the client, you are leveraging all of the learning that this client had to improve your global model iteratively. So now I think I'm going to sort of start with the open problems that I was talking about. So during the development of Visionaire, the first problem that actually I personally faced was the compression of the learning update. So as I said, as I explained in the initial stage, when we define federated learning, the learning from each of the model, that's from each client device, that's like an integral part to obviously improving the accuracy of your global model. And you want this learning to be frequent. You want this each client to be able to contribute seamlessly and like effortlessly and as quickly and as efficiently as possible. Now, this is obviously not the case always. So when you think of it in an actual setting, what is actually going to happen is that this learning content will be encapsulated in some file. And this file will have to be sent across, from your phone to the central server, like to the averaging server. And this exact communication pipeline, even this pipeline, if it breaks, then then your client is technically not contributing to the global model. So just to give you a little bit of context of what I mean by learning content and what I mean by the gravity and the weight of the content that's being sent across a network. I'm going to just give you an example of what we did with Visionaire. So in Visionaire, since it's an image-based model, our first intuition was, let's use a convolutional neural net, and we did. And we were working with images that were taken in 3K, 4K, resolution because they were taken on smartphones. And even after reducing them, even after reducing the dimensions in which we read the images to 64-bit by 64-bit, you can understand that the flattened feature vector was 4096, 4096 instances in one feature vector. And then, of course, we had other secondary features that was supporting this, only this image-based information. So there was metrological data, there was other kinds of data, hyperlocal data, and all of these concatenated would make a feature vector, which, as you can see, is about, say, 4107 instances. Now, when you feed this into even a simple connet, so we had like a 2-layer connet, this gives about 312,000 parameters, and that is a huge number. That's a huge number because the number of training parameters in your model is directly proportional to the file size that is being communicated to the server. So larger the number of parameters, larger is the number of, the larger is the size of the file that is being sent across the server, and more difficult it is for you to maintain the conditions in which this communication will be successful. So, it may be possible that this may be requiring a lot of internet bandwidth. It may be possible that your device would require a certain amount of charging just to send this file, or it may be possible that this device has to be idle and it does not have to be doing some background computation when it is sending this kind of this file across the server. And our solution to this was actually quite naive. We had to do a lot of research into the system that we were developing, so the AQI inference system using images. And eventually, what we had to do is that we had to update our model pipeline to include a pre-trained connet in the beginning, which would sort of give us some parameters that would be used in a deep neural net, which would finally do the inference for us. So the idea was that the local client, we can't train the local client we can't train a continent on the local client. So let's just try and dumb down the deep learning model on each client by making it a deep neural net. And to leverage the learning that the ConNet was doing for us, we just basically took some parameters, took a pre-trained ConNet. We trained that ourselves, but we took that and fed that into our DNN. And while it reduced the number of training parameters like drastically, it almost reduced the training parameters by 530 times. You can see that the training parameters were 591 after 3,12,000. But even if this did that, this is not a sustainable solution, because you're sort of dumbing down your model. And you also understand that, I mean, I'm sure all of you agree that you will not find these scenarios a lot of times where you can update your inference pipeline in such a manner that the model that's being trained on the client is much simpler than the model that has to achieve the actual objective for you. So this, in my perspective, is probably the first and the most common open problem in federated learning. Gradient updation and the learning content updation is actually a very common problem in federated learning, and there are there's work being done to reduce the effect of poor compression techniques. But that is sort of in my next slide, I'm going to sort of talk about federated learning architecture's compatibility with security aggregation. And here I'm actually going to tell you why sometimes compression, the effective compression of your model, is nullified because you're trying to make the communication secure. So as I mentioned before, and I'm glad that we've had Nick's talk before this, because he's talked about how the introduction of noise, how the introduction of even a little noise, epsilon, can actually create a massive difference in vector space. And in this case, if you see, like in federated learning, what ends up happening is that there are instances where we have observed that even if you're just sending the weights to the averaging server, there can still be a reverse engineering method to find the origin of the data and find the origin of and find some attributes of the client that is contributing to this data. Now, you can understand that this kind of reverse engineering is kind of beating the purpose of using a federated system, because if you're actually getting to know about the attributes of the data that's being shared, or you're able to get some attributes about the client that's sharing this data, it's no longer as privacy preserving as you claim it to be. So, and one of the ways that you counter this is that you add noise to the data. So we know that when you add a little noise to the weights that are being sent across to the server, they are no longer very unique. It sort of ambiguates and convolutes the data that is being sent now to the server, and makes it harder for whoever is trying to create a backdoor to find the origin of the data that's being sent across the server. And this is being done through like security aggregation protocols. There are cryptographic methods that you can do to achieve sort of like an encryption on the weights that you're sending to the server. And over and above, this will sort of do the job. This will hide the data in such a manner that a backdoor cannot be created for at least the majority of the weights that are being sent on the model. But here's the problem. In the context of data communication, noise, even in its rawest form, is also data, and it takes space. So if I give you like a simple example, like one of the basic versions of security aggregation protocols, what they end up doing is that like if you have M clients in your network, and you want to like encrypt your weights in a certain manner that they will be using the security aggregation protocol, you are convoluting the origin to convolute the origin of the data, you will at least have to include a big O of log M parameters with these, with the data that you're sending, in order to sort of ambiguate the data that you're sending. So for example, if you had like 2 lakh clients, by the mathematics of O log M, you would have to send 5 additional scalars for each parameter that you're sending. And this is a massive the communication overhead. So consider that you were sending 500 parameters before, but now because you need to, convolute the origin of the data, you're encrypting the data, or you're trying to add noise to the data. And here, when you're adding that noise, you are massively, like by 5 folds, increasing the size of the file that was being communicated to the server. So this in itself is again a massive problem within the federated learning domain, because communication efficiency and this communication bottleneck is the core of why federated learning systems may not be performing the best. Like when all clients are not able to contribute to the global model, your global model is obviously not going to improve its performance iteratively. And worst of all, it may become biased to the learnings that are coming from a few clients and may just, of course, like have like counterproductive training by just producing like biased productions over the learning that it's having over these clients. So this pretty much sums up the learnings that I've had from the project that I built. At this stage, I think a huge open problem in federated learning, as well as an open, like an opportunity for us engineers, is that federated learning is at the intersection of several domains. It's at the, it can use blockchain, it can use, it does use cryptography. It is at the domain of a lot of communication engineering problems. And henceforth, for a single architecture to be perfect in all these aspects, it's actually a little difficult. You're going to have a very diverse team working to develop certain architecture. And that's pretty much about it. I'm so thankful to PyData Delhi for giving me this opportunity to share my learnings from this project that I did. And that's pretty much it. If you have any questions, I'd be happy to answer. Thank you.
Yeah, all right. Thank you, Harshita, for the talk, and it was quite energetic. So I think we have some questions over the YouTube live chat. So I'm just going to shoot it over to you. So the question is, wouldn't client interface normally anonymize the data being sent to the cloud, similar to how telemetry data is sent to a regular app?
Yes, so that is the core of like the client data is like anonymous. That's why this is privacy preserving. There's no like, can you repeat the question? Are you claiming that client data is anonymous by default in a federated system?
So the question is, wouldn't client normally anonymize the data being sent to the cloud?
Oh,
so basically,
no.
He's asking. Okay.
No. Okay, so I think the question here is, can you anonymize client data to that extent? So when I say client data, consider this: when I'm sending an image of like something of something in my near surroundings that perhaps has two other people in it to a cloud server for some kind of processing, that image has information. Even if that information does not have, even if that image does not have information about me, it has the faces of these two people who I have coincidentally clicked in this image, and I'm sending it over to a data. So these people are like a part of the client data that I'm sending. And even if I anonymize my ID, like let's say I anonymize my name and I don't tell you the source of where the information, the source of where you're getting that image from, you are still going to be, the privacy of these two individuals who are captured in that image is still going to be compromised. And that is where essentially that there's an indirect data breach that can harm sensitive data of the user. I hope that answers the question. If there's other,
yeah, I think that answers the question. I think we have one more question for you. So the question is the global model using the aggregated logits from the local model, inferred logits? If yes, then how did you approach it, seeing it's hyperlocal?
No. So traditionally, the logits of the penultimate layer or the logits of the entire weight are like the logits are actually being used, like the weights are being used, aggregated, and then being sort of replaced in the model's actual weight. So for example, you had the weights matrices of the global model is actually being replaced by the aggregated and then averaged weight matrices of the client model. And to achieve this programmatically, what you would actually have to do is that every time a client trains his model, you would send, so if I talk in TensorFlow lingo, you would have to send the checkpoints file from each client to like a common server, an intermediate server. You're going to have to aggregate all of these checkpoints files because these would be the aggregated weights of all the clients. Then you're going to have to average these weights, and then you're going to have to replace the checkpoints file of the global model with this averaged checkpoints file. And this would eventually, this is the first cycle of how the global model parameters will be updated by the weights of the client models.
Yeah, I think that answers the question. And so yeah, I think there's one more question by Arnav. So the question is, do they all have to be the same model then? I'm assuming the local models.
Yeah, okay. So yes, that is why I specifically specified checkpoints file. So, if you see the TensorFlow architecture, you'll notice that when a model is saved, it's saved as, the meta file stores the graph of the model. And the general assumption in traditional federated learning systems is that the graph across the global model and the local model is the same. And I'll tell you why this, assumption comes by. Consider that you do not have the same client model on all of the devices. Would that not be a loss of information? Like, consider it in this sense. Let's say I'm client A and I'm training my model on a certain. I'm training my model on I'm training a different model, and that model is using different features. And another client B, is training another model, and he's training it on different features. Now you can understand that even knowing that I am contributing these features is actually a level of identification. Tomorrow, if you need to identify, okay, where am I getting this learning from? You can actually pinpoint and say that, okay, because this learning is probably coming from this feature, it is coming from this client. So in traditional systems, there is no level of identification that you want to give to the client model. You want an exact identical system all across the client models and the global model. And if you don't do that, so if you have this system where each model, where each client has like a different model that's being trained, then through the features that that model is using, that each client is using, you would be to some extent able to identify what kind of data am I contributing to the global model. Yeah.
Yeah, I think that answers the question and very well answered. So yeah, so as usual, I think I have one question from my side to you.
Yeah, sure.
So the question is like, usually like the local models are gonna send the weights to the central server. So is there any sort of security or encryption that you're using while sending the weights to the central server?
Yeah. So that's pretty much why I introduced the security aggregation concept. That's not the most robust concept, but yes, the idea is that when you're sending the weights, the learning content from your clients to the central server, you will employ some kind of either encryption technique. The most common of it is called homomorphic encryption. So the concept of homomorphic encryption is that even if you have encrypted data, so if you have encrypted X, encrypted Y, you can actually run mathematical computation between X and Y and get an encrypted result, which is actually going to be valid in mathematical senses. So the mathematical operation is going to be X and Y, but it's not going to be run on decrypted information. It's going to be run on encrypted X, encrypted Y, and it's still going to give you a mathematically valid encrypted output, which would, which can actually be scaled up to this level where you're taking weights from all of the clients, you're homomorphically encrypting them, you're aggregating them, averaging them, and then using that to update the global model. So in this case, the only entity that's going to be decrypting the homomorphically encrypted weights, average weights, is going to be the main server, and the main server will not have had access to the data or the individual client weights. So in that sense, also, it's not like you're breaching any of the originating client data link. So, and then there are, of course, other methods like security. There's a secure multi-party communication. There's secure aggregation, as I mentioned, where you add noise to the data, and that is also to some extent masking and making your and find the origin of the data. I hope that answers the question.
All right, yeah, thanks for answering the question. So Nick, do you have any question for Harshita?
No, I think not off the top of my head. I think you did a really good job explaining that. Yeah.
Oh, thank you very much.
Yeah, I think she was fantastic, and given the fact that it was the first talk.
Oh, that was the first talk. Oh, sweet. Very well done. That's great. Thank you.
Thank you. It's very nice of you. Thank you very much.
So yeah, I think that brings us to the end of this meetup. So I think so like we have a couple of volunteers who have been working hard for the past week or two to bring this meetup to you guys, and I would like to I would like to thank each and every one of you for the meetup. So as usual, like I don't know if you guys know my name. My name is Sanket Verma, and and I'm like one of the volunteers of PyData Delhi, and I lead the efforts of all the like conference meetups and everything. So I mean, I would highly appreciate if you guys could do a quick introduction of yourselves, like the hands behind the scene and the efforts behind the scene.
Yeah, hi. Hello. Can you hear me?
Yeah, sure. Laksh, go ahead.
Yeah, hi. My name is Laksh, and I've been with PyData since 2017, early PyData Delhi, and we have been doing conferences and meetups and everything. The only thing that I would like to say is that since we are having virtual meetups, I think anybody can, whoever is listening right now, will listen to it later on YouTube. They can just contact us on Twitter or like Telegram chat and just ping us if they wanna give a talk. So, I mean, that would be great. And we would love to hear different speakers' talks or something like that, or project showcase or lightning talks, anything at all. Yeah, and that's it.
Yeah, definitely. Thank you. So over to you, Chetan.
Yeah, hi guys. My name is Chetan, and I've been with PyData Delhi for the last year. So I've been involved with almost everything that we do here, and we do a lot of things. So we, like as Laksh
Yeah.
said, we do the conference, we do meetups, we do lightning talks. We are about to announce more things coming our way. So have a look out on like the Telegram channel and join us. Over to you, Harsh.
So yeah. Harsh, over to you. Okay, all right. So over to you. Yeah, over to you, Gaurav.
Hey guys, I'm Gaurav. So I've been a volunteer for PyData for the last 3 years now, and I'm really interested in the things coming our way. Sure. Over to Mutasim.
Hello guys, I am Mutasim and I have joined PyData last year for the conference work and I'm still connected with them. Although I haven't done anything for this meetup, like I'm just taking the credits Sanket is giving me, and I'm also doing some stuff in web development and full stack development. So it's like a very good community and I feel so good and the people are so welcoming in this community and everyone is welcome to join. Whosoever is listening to this talk. Yes, thank you.
Yeah,
Now,
thank you. And I think Harshita introduced herself, and I think there's one more guy who is missing from the call. His name is Raman, and I think he's not feeling well today. So, but yeah, Raman has been good good amount of workforce between for the PyData Delhi, and yeah, this is pretty much all of a team. So just a small quick thing that we have a feedback form, and I think the link for the feedback form would be on your screen right now. It should be on the bottom of your screens. You can just go over there and fill the feedback form, and that would be super helpful to us. Yeah. So I think that brings us to the end of the meetup. And
Oh, by the way,
thank you, Nick, for joining us. It was super fun to have you, and a huge pleasure. And yeah, I hope all of you guys enjoyed the meetup. So
yeah.
I think that
Also,
we can end the live stream
I,
now.
yeah,
And Nick, if you want to stay, you can stay.
Hello, can you hear me?
A second, can you hear Laksh?
Hello. I think Sanket is gone.
Oh.
Yeah, I thought like it's my connection. Anyway, so I was just saying that people are been saying that they want quizzes and everything. So guys, we already hosted quiz twice already. We are thinking to do something else, but we don't have exact idea what would be good at this time. So maybe you can give a suggestion over Twitter or Telegram chat and everything. And we will be doing probably 1 week or something like that kind of machine learning question or something like that project or like small case something maybe soon. So let's see what goes. You guys can just ping us some suggestions if you guys want anything at like just tweet at PyData Delhi. That's it. And I think Sanket connection was lost, so like he was just going to end the call. So let's just end it. And thank you for everybody joining us here today. Yep.
Thanks. Yeah.